In the previous movie, we looked at the t-test that was used to compare the means of two different independent samples. In this movie, we'll look at another common variation of the t-test, the paired t-test, where you compare one group before and after. In this example, I'm going to be creating some random data to demonstrate exactly how big the difference is. What I'm going to do here is I'm going to create a variable called t1 for time 1, and I'm going to be using the random normal function, which means I'm going to be pulling data from a random normal distribution. I'm going to get 50 observations, 50 cases, and I'm going to use a distribution with a mean of 52 and a standard deviation of 6. And so there I've got my numbers right there. If I click on them, there you can see they all are. Your numbers will be different, and if I run this again, I'll get different numbers. It's a random process. Now what I'm going to do to simulate change over time, so for instance before and after an intervention, is I'm also going to create a variable that gives the difference for each person from time 1 to time 2. So that's going to be a variable called diff for difference. It's also random normal. I'm also getting 50 scores, except this time, because I'm using a change, I'm going to use a smaller mean, a mean of 6, but I'm increasing the standard deviation to 12. I run that line, and now I have diff showing up in the workspace. And then I can do a little bit of vector math, which R makes very easy for us. And I'm going to create the time 2 scores for each person by adding the time 1 score and the difference score. And because of the way vector math works in R, all I got to do is say T1 plus diff. And now I've got all 3 of those for each person. I'm going to do some quick plots. First, let's do a histogram for time 1. All right, that's basically a normal distribution, which is what I would expect because I got samples from a normal distribution. Here are the difference scores. By the way, this is actually going to be the most relevant distribution for what we're going to be doing because I'm looking to see whether the difference scores are significantly different from 0 as a whole. You can see that it is biased towards the positive side. That's because the mean is 6, but we're going to see how the inferential test works and whether it is significantly higher than 6. I'm also going to look at the time 2 scores. Slightly skewed, even though it was drawn from 2 normal distributions. We can look at side-by-side box plots of 1 and 2, and you see that the time 2 scores are much more spread out, which makes sense because we combine them with a second distribution with a standard deviation of 12 as opposed to the original of 6. Now, the most relevant chart for a time 1, time 2 comparison is actually not this box plot because you need to know which score goes with which. That would also lead you to think that a scatter plot was a good thing, but a scatter plot, it's a little hard to tell exactly whether it shows an overall improvement or not. Instead, I'm going to use something called a parallel coordinates plot, and I need to use the mass package to do this. So what I'm going to do right now, actually I'm going to also get the data set into a single data frame. That's how mass wants it. So I'm just going to use this one. I'm going to create a new variable, a new data frame actually called pairs, and then I'm using the function data.frame to combine these 2 variables, T1, T2, into a single data frame. So I'm going to run that one, and if I just click on this over here, you'll see now I've got 2 rows, T1 and T2, 2 columns, and 2 rows per person. Mass, I believe, is installed by default, and all we have to do is load it by using require our library mass. And then here's how we do the parallel coordinates. The function is pairCoord, and you can do just pairs, but by doing the var label.true, it'll label the minimum and maximum of each of the 2 variables, which is handy. So I'm going to run that, and it looks like a bunch of pickup sticks scattered all over the place. The question is whether, on average, the lines which connect the scores on the left to the scores on the right for each person, that's time 1 on the left, time 2 on the right, the question is whether the lines on average are going up or down or whether they're flat. Now, truthfully, these ones look overall pretty flat. We'll see if my random data in this case does or does not support my hypothesis. Let's do a quick paired t-test. This is how you do it. Use the same command t-test and you set up the 2 variables T2, T1. You want to put the later one first. And all you have to do is this second part that says paired equals true. That's what separates the independent samples t-test from a paired samples t-test. When I run that, here is my hypothesis test. And what's interesting about that is even though it's really hard to tell whether there's a difference here by looking at this mass of lines, it is in fact statistically significant. The value of t is 2.9, and with 49 degrees of freedom, that gets us a p-value or probability value of 0.005. So it actually is strongly significant. This is one of the times where having a little numerical analysis can make life easier because I could not have told you by looking at that chart whether it was significant or not. Now again, because the data is drawn at random, your chart will look a little different, your values will be a little different, and the results of your t-test over here will be a little different. but we know that there is a change in scores, at least in the population, because of the way I calculated the scores right here by saying that I had a mean change of 6 points. So we would expect that on average to work out. Now I'm going to do this test again just with a few different options. What I'm going to do in this case is I'm going to use the same command t-test. I'm still specifying time 2 and time 1 as my variables. I'm still saying paired is true. But now what I'm going to do is I'm going to give a non-zero value for the null hypothesis. That's mu, that's the population mean. This time I'm going to say, is it different from 6? And the reason I chose that number is because that's what I said the difference would be when I created my formula for getting the data. And I want to see whether it's significantly greater by doing a one-tailed test. And I'm going to do a confidence level of 99. So I can highlight that block of code and run it by pressing Command Return. And what we find in this case is, interestingly, that it is not significantly different from 6. Now that shouldn't be too difficult because actually 6 was what I asked it to sample from. And so we're basically with a t-value of minus 0.71 and a p-value of 75. That tells us there's a 75% chance of getting a difference this big if we're sampling from a distribution with 6. So that is what in fact happened. In any case, that's how you can do a paired t-test comparing scores for the same group of people before and after a particular intervention. Again, one of the most common statistical tests in experimental research and probably going to be a great use to your own research.